Okay. Oops. Ooh, I didn't realize it was there. Our next speaker is Maksym Radziwill.
Thank you for the invitation. So I'm going to talk about exponential sums over primes, a very classical topic in analytic number theory, maybe one of the most classical, since you see this in introductory books. So the topic concerns this sum, the sum of e to the 2 pi I alpha p. So this is kind of, you consider this if you want to obtain results about equidistribution of alpha p modulo 1. And Vinogradov was actually the first to obtain anything non-trivial on the sum. Basically, he showed cancellations in the sum as x goes to infinity. And why did he do this? There were actually two applications at the time. And there's one application showing that alpha p modulo 1 is equidistributed as p goes over primes. So that's the analog of Weil's result that alpha n is equidistributed, but for primes. And the other application was his famous result that any sufficiently large odd integer is a sum of 3 primes. So this was the second application of Vinogradov. And you might at this point object, I mean, don't we need something stronger cancellations in the sum to obtain 3 primes? But I think with modern technology, that's actually enough. You just need to consider 3 and then take out half a moment and use a Majorant principle on 2.5 moment. So unless Trevor objects. At the time even, okay, great. So then, okay, so then those are two applications, and these are two applications of this result, but generally any kind of additive problem that involves primes is very likely to encounter the need to bound this sum. Okay, so now if you're not familiar, I kind of want to walk you through what to expect for the sum. So what is the actual conjecture that we expect to be true for the sum? And if you want to make a conjecture for the sum, you need to distinguish two cases. So the case of alpha being exactly rational, and then the case of alpha being as far away from rationals as possible, so alpha being the golden ratio. So let's start with the case of alpha rational and see what we expect for the sum. Okay, so I'm going to also suppose that the denominator is prime to make my life a little bit easier. And if you want to understand this exponential sum, the easiest thing that you can do is just split into arithmetic progressions modulo q. So if you split into progressions, then p is congruent to L. So basically you can replace p by L, and you can move the sum, the oscillating sum, outside. So the entire question boils down to a question about equidistribution of primes. And since I'm in the purely heuristic territory, I can just tell you what is true. And what is true, but we cannot prove, is that this is basically just the primes and the chunk 1 over pq of them, plus an error term, which is square cancellation in the number of terms. That's actually what should be true. So what the Riemann hypothesis gives you is actually square root of x, but what is actually true is square root of x over q. But that is beyond anything that anybody can prove. And then what is also this? This should be some kind of random variable that oscillates in some chaotic way and is bounded by x to the epsilon. So this is actually what is true and what we cannot prove, because even the Riemann hypothesis only gives you square root of x, which is a very big bottleneck in the subject. We can just get square root cancellation in the length of the interval, not in the number of terms. Okay, so let's assume this. And then what we do is that we take this sum over primes E AP over Q, and I insert my heuristic about equidistribution of primes. And what do I get? Well, the main term is actually constant. It's always 1 over PQ number of primes. I get cancellation almost over the entire circle. But notice one thing, 0 is missing. And 0 is missing because there are no primes congruent to 0 mod Q, other than 1. Sorry, yeah, other than 1, Q. Yes. So, and Q is prime. So this is why the sum is missing one term. And that's actually very important that one term is missing, because it actually creates a main term. It's not perfect cancellation. You see, primes don't have perfect cancellation because they're actually primes. And then here, what do we expect? Well, this is a random variable, it's chaotic. So this is like square root of q. By the central limit theorem, this is basically square root of q. So you end up with actual square root cancellation. So this is the actual conjecture for this sum. This is what we believe to be true. And you see that after q is bigger than square root of x, this overwhelms everything. You just see pure noise. Nothing interesting is happening anymore. Okay. So one thing that this actually tells you is that the quality of the rational approximation will matter in the general case. So let's now consider the general case. I'm going to pick alpha irrational, and I'm going to use Dirichlet's theorem. So I take any alpha irrational, and by Dirichlet's theorem, I can find a fraction which approximates it with error 1 over q squared. And I can make q less than square root x. Why do I make q less than square root x? Well, you see it already in this heuristic. Taking q bigger than square root x makes no difference for bounds. That's a good place to stop. Okay, so if we do this, I can write my exponential sum as this, what I already understood, times theta p, which I don't understand. And what is the easiest way to handle theta p? Well, you can actually cut the sum into short intervals, and the intervals, you make them short enough that this theta p doesn't actually cancel out, doesn't have any cancellations. So let's actually do this. So this theta is bounded by 1 over q squared. And what I'm going to do, I'm going to just cut this into intervals of length q squared. And on each such interval, this does not oscillate, which means that I can apply my previous heuristic, but just on every short interval to see what I get. So let me actually do this. So I'm going to take the sum and I split it into intervals of length q squared, so that on each interval, this theta p is constant. So then I can repeat my previous heuristic. I'm looking at a short interval, and what I expect a main term, which is this, plus square root cancellation, which is just q. So this is what I expect. And then I have x over q square intervals. So I can sum over these intervals. When I do this, I recover the main term. And then I have x over q squared times q. So I end up with a bound which is x over q, even in the general case. Okay? So this is actually the final conjecture, which we believe. And we believe that this sum should be bounded by x over q plus square root of x. This should be sharp, and this is the final truth about this exponential sum. This is what we believe to be true. Okay, and right. So then also notice one thing, that if alpha is a quadratic irrational, you can actually choose q to be of size square root x, and then you get exactly square root cancellation. So that's what's actually believed for, let's say, square root of 2. Okay. So now the question is, what can we actually prove? So we are actually not doing that poorly in general. So this is one thing which is nice, is that if you stay away from multiplication in analytic number theory, you can often do quite well. So, and this is surprising, right? We can often maybe even do better than Riemann hypothesis. Like, for example, for bounded gaps between primes, there's no way to do that through zeros. But we can actually do it, we can actually go beyond, in a sense. Okay, so here the situation is maybe a little bit similar. And here is actually what can be shown. So what we can show, it's a little bit worse, but I think it's not terrible. So what we can show is that instead of x over q, we have x over square root q. And instead of x 1/2, we get x to the 4/5. And I call this a success, because it's a power saving and roughly the correct shape of things. Maybe not the correct exponents, but at least the correct shape of things. So this is a very old, this is a very old result of Vinogradov from 1937. And just before preparing this talk, it occurred to me that 1937 was a very tough time in Russia. It was the Great Purge. So he was somehow producing during this turbulent time. Okay. So here is kind of the main result that this talk is about. We can improve this exponent a little bit, this 1924. So we can lower this 4/5 of Vinogradov, by basically 1 over 120. And the point is like just the first improvement in a long time. So that's the point. But what I want to do now, because you see these are exponents, so if you don't know where these exponents come from, this looks like a heavy lifting sport, and I look like a Olympic athlete and just showing off my muscles. But I want to explain that these exponents are actually meaningful. So both of these exponents are meaningful, and this is actually very meaningful, and this is also meaningful. And so what I'm going to do, I'm going to explain where these exponents come from, and this will actually motivate the improvement of that exponent. Okay. So let me start with this x over square root q. That's okay. So the way where x over square root q comes from, it actually comes from C-go zeros. If you can improve this, you can rule out no C-go zero. So how do you see it? Well, what you do is that you can take the additive character and you can open it into a multiplicative character, chi mod q. And the price to pay for this, I mean, this is a very unnatural thing. You're taking something additive, making it multiplicative. And when you do something unnatural, you pay a price square root q. The Fourier transform, because the Fourier transform doesn't take any pity of you, and it's just random, and it's square root q, square root cancellation. So this is a general fact of life. If you take one thing, make it into something unrelated, you will pay square root of the complexity. And here complexity is q, the conductor. Okay, so now that we have this, what I can do, I can just sum over primes.
Statement of Nagrado and then your improvement. Is Q prime?
No.
Or is it just in your
anything? Yeah, Q is anything. Just anything like this.
But it was only before in your
Yeah, this was just to make things easy because then I have only L congruent to 0 mod Q to worry about. Okay, so what I do, okay, I sum over primes, I'm getting this expression. And now notice this is something that can be understood through functions. So this is what we're going to do. So assume that there is a C-go 0. If there is a C-go 0, then there's a 0 very close to 1 for a quadratic character, which means that L1k is very small. And if L1k is very small, it means the order product is very small. And the only way that this can be small is if you have chi p close to -1 for the majority of primes p. So what happens in this decomposition is that if there is a C-go 0, then look at the quadratic character, and this one quadratic character contributes basically x over log x here, minus x over log x, and assume that the C-go 0 is the only obstruction to generalized Riemann hypothesis, which could be a fact. That could be. And if that happens, then the only character that contributes is the quadratic character. It contributes minus the full sum. You get tau of chi of the quadratic one, and you get this. So basically, if there is a C-go 0, there is a genuine main term of size x over square root q. So we don't know how to get rid of this without getting rid of C-go 0. Okay, so this is where x over square root q comes from. And of course, C-go 0 is very rare. So you can show that for the vast majority of moduli q, this term can be, this shouldn't be surprising. It's really for very few sparse q that this x over q is actually there. Okay, so now let me discuss the 4/5. 4/5 is also motivated. It's not kind of a random coefficient. So this is a principle in prime number theory. When you want to prove something about primes using harmonic analysis, you usually start with what is known as Linux identity. And what Linux identity morally does is that it takes the indicator function of primes and writes it as a big linear combination of divisor functions. So essentially, kind of the first test that you do to see if you can prove something is to check if you can prove it for every divisor function. And if you can do that, you can probably do primes too. So let me kind of do this. And instead of working on this, let me work on the k divisor function. Because this is a prerequisite. If you want to obtain a result about primes, you should be able to obtain a result for every divisor function. And then Linux identity allows you to actually do primes. It's just a matter of technique. So let me focus on this. And in the literature, these are called decay sums. They're called type decay sums. And okay, so there's kind of a counterintuitive thing happening with them. Usually k equals 1, everybody can handle, very easy. And then k equals to 100 or 1000, we can also handle. And it's usually some intermediate k which actually poses a difficulty. And it poses a difficulty because this is kind of hard to jam into every range that is available. So I'll explain. So one more thing, so the divisor function, the actual hardest range is usually when the variables are symmetric. If they're unbalanced, you can usually make use of the longest one and there's some game to play. So often actually the hardest range is when they're all of the same size. So where is the 4/5 coming from? It's actually coming from this configuration. It's called type D5. This is where this bottleneck is coming from. And so let's try to bound this type D5 sum. And the standard technique is to make it into a bilinear sum. So I'm going to group 3 variables, and I'm going to group 2 variables. So then I rewrite this as a bilinear sum with a of size xi over 5 and b x1 minus I over 5. Those are the configurations I have available for me. Okay, and then so this is the move of Vinogradov. You have a bilinear sum, you Cauchy-Schwarz. What's the point of Cauchy-Schwarzing? You can sort of replace this by a smooth coefficient. That's kind of like a matron principle. So we're going to do get cancellation in this by applying Cauchy-Schwarz. Okay, and you see that's kind of a matron principle because now the sum over A is smooth. Before it was complicated, and now it is smooth. So this is the advantage of Cauchy-Schwarz. But the price to pay is that I increase the complexity here because I have a... Okay, so then we have to bound, this is what we have to bound. Well, there's no cancellation to be had here. You can only have cancellations here. You can assume that this is random. If this thing is random, then the best you can get is just square root cancellation. That's the best you can get. So the best that this can be is just square root of b. So the best bound that you can get for this is actually x over square root b. That's the best you can do. And your choice of b is quite limited. B has to be of this shape, right? So, okay. And then when can I prove this bound? Well, to prove this bound, I need this family, the size of A, to be bigger than Q. And Q can be of size x to the 1/2. So this means that A needs to be bigger than x to the 1/2. But if A is bigger than x to the 1/2, B is less than x to the 1/2, and then the largest B that I can take is 2/5. And then I can get square root cancellation in the sum over B. So I can save exactly x minus 1 over 5, and that's the 4/5. That's actually where this is coming from. That's the bottleneck. Okay, so if you want to go beyond this, you need to go beyond bilinear methods. So to go beyond bilinear methods, you need first a formula that's somehow multilinear, right? So the only way to do this is to actually open this into characters. And what we do is that we open this into Dirichlet characters and this into DIT characters. And so you have this kind of formula where you see you pay square root of Q here because you're doing something unnatural, transforming this into Ka. And here you're also paying square root of T because you're transforming theta into N to the IT. So you pay square root of T in both Fourier transforms, except that this is a finite field Fourier transform, and this comes from stationary phase, right? So oscillatory. Okay, and so now the question is bounding this type of expression. And so what is the idea here? Well, the idea is to appeal to the recent breakthrough of Good-Maynard. But there's one catch. This result of Good-Maynard only works in the T aspect, not in the Q aspect. So what we need is a generalization of this result to Q and T aspect. And so what happened is that I had an undergraduate student and I told him, do it. And James also had a graduate student and told him, do it. And then we found out that they're both doing it for the same reason. So this is why it's a joint paper. And Mayank also, I mean, we found it kind of independently, I mean, with Mayank. And then I told the undergraduate do it, and James actually also had independently, and that's why it ended up being a joint paper. Okay, so roughly we need, to handle this expression, we need large value estimates for this, which are similar to Book-Maynard. So this is a bit technical, not so important. So there is a C bound for large values of this shape. That's what we use. And this is actually what gives this result. So it's just a technical large value estimate which gives this. And okay, so this is the final result. And there's one kind of little catch. So what we actually prove is x to the epsilon. There's an x to the epsilon in front of x over square root. If you are working in explicit number theory, you are probably very upset about this and you want to remove. So there is a very big literature of people removing this in front of this term with various constants. We don't care about this because this is already done for small q. You can remove this. And for big Q, we see no reason to actually remove it because you're just, anyway, what's the point? So this is why we are okay with this term, but there is an x to the epsilon dash. Okay, so here are some open problems that I want to advertise, which are unrelated to my main result. So one embarrassing thing is that assuming the generalized Riemann hypothesis, the best we can do is 3/4, not 1/2. So getting 3/4 minus delta would be a great result, assuming generalized Riemann. Even more annoying if you look at square root p. For square root p, this is known unconditional. But this would also be a great result because it would actually establish a positive proportion of simple zeros of GL2L functions. This is hard to believe, and it always takes me 1 hour to rederive it, but it's true. And the square root p comes from the fact that you're twisting by GO2. So there is a e to the it log t, you integrate n to the it, you get square root p. And this actually comes from the application of explicit formula to GO2. And you genuinely need the power saving. Okay, why is 3/4 a bottleneck? It's because we use Cauchy-Schwarz. If you use Cauchy-Schwarz, you're always losing 1/4 of your saving. It's gone, nothing you can do. So this would be a genuine breakthrough because you would actually show how to go beyond this bilinear method. Plus, even if you assume Lindelof, 3/4 is also a bottleneck. If you transfer it to characters, you also lose 1/4 from the Fourier transform. So to go beyond this, you need some cancellation between these Fourier transforms. Nobody knows how to do it. Okay, and then there's also a question about varying Goldbach problem, which we didn't consider. I think what we did might not actually apply. I don't know. And yeah, because I think it's outside of the range, maybe outside of the range of the good. I didn't think about it. Maybe, yeah. Yeah. Okay. But I just never think about varying Goldbach, so I just don't know. I never thought about it. All right, thank you.
P over 24 is about half of 1 plus 7/12, isn't it? It is, that's true.
Okay.
So when you wrote down 19 over 24, I was expecting maybe a half of 1 plus 13 over 30.
Okay, that would be nice, actually, yeah. Yeah, we could do that. Yeah,
Right.
we could write it this way. Yeah.
It's 7/12 is Huxley.
Yeah, that's right, actually. Yeah, that's right. That's right. Yeah. Yes. So what happened is, with Mayank, we noticed this before, and then we had this task of actually proving this for this Q analog. No. So, well, okay. So this discussion of this started when Mayank was an undergrad, and some observations were made. And then after this good Maynard emailed me, he said, "Oh, actually, we can do it now, thanks to good Maynard. We just need to generalize it." Okay, but by then he was a PhD student. Okay, but then you see, then we had the onerous task of proving this Q analog, which I didn't really want to do. So I had a good undergraduate student. I said, "Why don't you do it?" And then And then, he did a good job, but he kind of went into finance. So, but James had another first-year graduate student who was tasked with the same thing, and then they formed a team, and we are still waiting on them to finish, actually, this Q analog. So, okay. So this is kind of the story. Okay. So this is not put on YouTube, right? I hope. Yeah. I mean, it's okay, but I just kind of don't want to, I want to be diplomatic and make sure. Yeah.
I have another question.
Yeah.
So it's Alexander Kalminin. So
Okay.
question is, if we say assume that there are no Ziegel zeros, or for example, we can take some combination of our sums so that Ziegel zero terms cancel out. Is there any hope of improving x over square root of q?
Yeah, I mean, if there's no Siegel zero, I think you can get, right away x over q times exp minus square root log q type of thing. That I'm pretty sure. Whether you can get a power saving, that is less clear. Whether you can get a power saving over square root q, I don't think so, actually.
Yeah.
Other questions from Zoom or the room? If not, thank you.
Thank you.
Fabulous result. It's yours? Thank you. So let me give you mine.
Very nice. Yeah.